So in the earlier lecture, I talked about coordinate system and law of triangle law of vector addition. So and position of a particle in the coordinate system, and I also talk about parallelogram law of vector addition, and it is related to triangle law of vector addition. So let us have a look at the parallelogram law of vector addition. Suppose we are having two vectors. The one vector is A. This is one vector A. Just a minute here. This is one vector A. It's represented by A vector, and there is another vector. Let us recall it as the vector B. Suppose these two vectors represents the two adjacent sides of a parallelogram. So what I will do, I will just I just copied it. I put it from let me just a minute. Let me copy it from here. I just copied it from here and say this represents the adjacent side of a parallelogram. So say it is like this. So these are the two vectors. So what I will do, let us, using these two vectors, let me complete the parallelogram. So parallelogram is completed like this. So I just picked it from here and put it here. So this is like this, and similarly let me bring this B vector from here again. This is the B vector, so let me copy it from here, and so if you copy it from here, say it is like this. So this completes this parallelogram. So these are the two vectors which are given to me. So I completed a parallelogram with the help of this. And if I try to look at this part, because this vector is parallel to this vector and this vector. So I just completed this. So if I try to look at this one part, as I see here, say if I try to see this part, so this part is basically looks like a triangle, and here A and B vectors, one vector is this is another vector, these both are along the same direction, means both are not in the same direction, but both the vectors are taken in same order. So then the resultant is basically the third closing side, but what was taken in the opposite order. So that means this is the resultant vector. So this R is equal to nothing but A plus B vector. This is according to triangle law of vector addition. But if I look at this figure as a whole, then it's a parallelogram. Then what it suggests for me? It suggests for me that if two vectors represents, because this A and B, this is one vector, this is another B vector, these two vectors represents two adjacent sides of a parallelogram, then their diagonal represents the resultant of these two sides, or the resultants of A and B. So this is the parallelogram law of factor addition. And we can also elaborate this for the polygons. So suppose we are having a polygons like this. Say one vector is this one. This is one vector A, and this is another vector B, and say this is another vector C, and say this is another vector D, and this is another vector E. Then, and these all the vectors are taken in same order. Here I can also apply the triangle of vector addition also successively. First of all, I will apply triangle of vector addition here, and then this third closing side, this is R, it is the resultant, it is the sum of all these vectors, means R is equal to A plus B plus C plus D and E. This is the resultant of all these, because this is the last closing side, it is taken in the opposite order. Say this we can prove by by using basically a triangle of vector addition. Because if I take A and B and say it is the third side, then it is taken in this order, then these two vectors is basically the sum of this vector is basically the sum of A and B. So that means this is represented by A plus B. So this is one vector and this is another vector, so these are also in the same order. So that means now this vector is basically the sum of these this vector and this vector. So this is A plus B plus C. Now these vectors, because this is one vector, this is another vector, and these are taken in the same order, then this vector is basically represented by A plus B, means this vector, and this vector is nothing but A plus B plus C plus D vector. So this vector is basically sum of these two. Similarly, if this vector and this vector are taken as the sides of a triangle, then the opposite side or the third closing side, which is taken in the opposite order, can be written as a sum of these two. So that means this vector, this R, comes out to be A plus B plus C plus D, means this vector, and last one is this vector. So this way we can find out the resultant of all the vectors. So this is how we can relate our triangle law of vector addition, or how triangle law of vector addition help us to derive parallelogram law of vector addition and polygon law of vector addition. Right. So now next part which I am going to talk about today, it is the position of a vector first of all in a coordinate system. So the first is the position vector. In two-dimensional and three-dimensional space. So first of all, let me consider a two-dimensional space, the two-dimensional coordinate system. So yeah, so I have to talk about the coordinate system. Yes, let me first of all, so suppose this is a floor, this is x-axis, and say this is y-axis, and suppose first of all I moved along x-axis, say one step, this is first step I moved, this is another step, and then 3 and then 4 and the 5, so I moved 5 steps along x-axis, so that means I am here, and then I moved 3 steps, so one step is here, another step is here, and another step is here, so I am somewhere here. So I moved 5 steps along x-axis, and similarly I moved 3 steps along y-axis. Then I am somewhere on the floor here, so that means I am at this point. So that means overall I have moved to this point. So finally I reached at this point. So this is my position. So these are the two different ways to approach this point. Either I go directly or either go this way. Because as I discussed in the earlier lectures that Cartesian coordinate system is a more helpful, and the force shows the different response along different axes. Say x-axis it is showing different, means if force is acting along this direction, so that means it is contributing few towards means a certain amount of force is acting along this direction and certain amount of force is acting along this direction. So that means we need to describe because we are moving from this point to this point, so that means I have to express this position in terms of x and y. So I can represent it vectorially also. So if I want to represent it vectorial, so that means I am moving, first of all I reach at this point, and then I go to this point also. So I call it as, because I am moving along x-axis, let us call it as xi cap or the x vector, and I call it as a yj cap. Then if I apply a triangle law of vector addition, then I call this as a r vector, and this r vector is nothing but it is the this r vector is simply the sum of vector along x-axis and vector along y-axis. This is the sum of these two. Rather than I can call it as x vector or I can call it as y vector, just for the sake of simplicity, or I can write it down at like this, because x represents the how much I have moved along the x-axis, and how much I have, y represents how much I have moved along the y, and this I is basically the direction. So rather than calling it as a x vector and the y vector, rather better to represent it like this, xi cap and the yj cap. In some text, sometimes the direction of the axis is represented by ex cap and ey cap and the corresponding magnitude. So you can also see it like this in various textbooks also. So both are representing same thing. So that means I cap or ex I cap both are the same. Basically these are the unit vectors. I cap and the j cap, these are the unit vectors along x-axis and the y-axis. Means these are representing the direction of x and the y. And then if particle is changing its position from one point to the another, then its position vector will change. For example, So suppose the particle is somewhere here. The particle is at this point initially. So it is represented by this vector. And after some time particles reaches at another point, and say that point is so now the particle reaches at this point after some time. Say this is R1 vector and this is R2 vector. So particle is at time initially, at time t is equal to t1, particle is at this point, and after some time particle reaches at this point. So that means it is the initial point, and after some time particle reaches at here. So that means particle moved from this point to this point. So that means it has been displaced from one point to the another point. So this is called the displacement vector. This is called displacement vector. Yeah, just a minute. So this is called displacement vector. This is one vector and this is another vector. So say this vector is along this direction, and this vector is also along this direction, and this vector is along this direction. So that means this vector, say it is, let us call this point is O, this point is as A, this point is B. So that means the position of point A is called OA vector, and let us represent it as Y R vector, and similarly OB vector is represented by R2 vector, and the particle is displaced from A to B, so it is represented by AB vector. And what is this AB vector? If I try to look at this triangle OAB, then both OA vector and AB vector both are along the same direction, and this is the third closing side taken in opposite order. So that means according to triangle law of vector addition, OA plus AB comes out to be OB vector. So that means this displacement vector is basically, this is AB vector, this can be represented as OB vector minus OA vector, right? So this is where that how a position vector can be represented in a coordinate system, right? So this is the position vector, and sometimes we call it as the R12 vector because we are moving from first position to the second position. So that means R12 vector, it is the position displacement vector because particle is displacing from one point to another point. So it is represented by R2 minus R1 vector. Means final minus initial. This is the initial position. 1 is the initial position and 2 is the final position. So it is represented by like this. So it is basically final minus initial. This we have to remember. This is a very important thing. Now let us express this in terms of their components or the constituents, because along x-axis different components are there, along x-axis, y-axis they are different. So for example, if I try to look at this point A, so A point is basically represented by 5 along x and 4 for this. So it is the 5 4. So we can call it as the 5I cap plus 4j cap. Similarly, sorry, this is not A, but this is R. This is R vector, R1 vector, and similarly, let me correct it. Yeah. So this is R1 vector, and similarly R2 vector is represented by, because here it corresponds to the 7 and it is 10, so it is 7I cap plus 10j cap. So it is represented by R2, 7, 10. This is another way to represent these vectors also, because here it is a 7 and here it is a 10. Say, let me draw it, or I can draw a perpendicular from this to this. Say this is one point, this is another point. Similarly, I have this one point and this is another point. So this is basically 5-4 position. This is basically a 5-4 position, and this is basically a 7-10 position. So if I put these values here, so it can be represented as 5I cap plus 4j cap. No, R2 will be first. So that means R2 vector is 7I cap plus 10j cap minus 5I cap plus 4j cap. Now when I have to do little algebra, so that means I will be added or subtracted with I, and the j will be added or subtracted with j. So what it will be? It is 7I cap minus 5I cap, or I can put the components corresponding to I together. So 7 minus 5I, this 7 and this minus make it minus. Similarly, I can plus 10 minus 4 j cap. So the resultant vector comes out to be, it is 2I cap plus 6j cap. So this is our displacement vector, and this is also clear from here also. If I try to look at this distance, so how much is this one? This is 1, 2, 3, 4, 5 and 6 along y-axis, and along x-axis it is this one. This is the 2 vector. So this is 2 distance in magnitude along x-axis, and along y-axis it is the 6, right? So this is a way that how we have to determine the position vector. Also, when I have to find out the position vector of R21, say if I am interested to find out the position vector of R21, then for that what I have to do? R21 vector. So that means in this case R2 is the initial position and 1 is the final position. So it is represented by R1 minus R2 vector. So how this can be calculated? So that means R1 vector is this one. So it is 5I cap plus 4j cap minus 7I cap plus 10j cap. So what it will be? It is 5 minus 7. It will become minus 2I cap, and it is 4 minus 10. It is minus 6 j cap. So if I take a minus common, so it is 2I plus 6 j cap. And what it will be? This is basically the R12 vector. So it is minus of R12 vector. So that means if if this is a R12 vector, because this is identical to this vector AB vector. So it is R12 vector. Then R21 vector must be in the opposite direction. That's what we have seen here. So it is R21 vector must be same, but it was taken in the opposite order, as it is clear from this particular diagram. So if I have to generalize this concept, then let us call R1 vector, it is equal to xi cap, yj cap, and z. Let me talk about first of all 2 dimensions. And R2 vector is represented by R1 is x1 I cap and y1 j cap, and R2 is x2 I cap and y2 j cap. Then R12 vector can be written as R2 vector minus R1 vector. So it is x2 I cap y2 j cap minus x1 I cap minus plus y1 j cap. So it can be written as x2 minus x1 I cap plus y2 minus y1 j cap. Right. Similarly, R21 vector can be written as x1 minus x2 I cap and y2 minus y1 j cap. So this is the position and the displacement vectors in the 2-dimensional space. So I talked about here position vector and displacement vector. In 2-dimensional space. Now let me talk about the position vector and the displacement vector in the 3-dimensional space. So suppose this is a coordinate system. Say it is x-axis, it is y-axis, and say it is z-axis. Say particle is somewhere in the space, say suppose in a room. So it is let us assume that it is a floor. For the sake of simplicity, let us assume that this is a floor. Say it is y-axis, it is, say it is little bit extended. Yeah, so it is a y-axis. So it is the floor. It's a floor. So it is perpendicular to this, it is perpendicular to this, and it is perpendicular to this, and it is also perpendicular to this. So say it is a floor, and this is the height of a room. It's the height of a room. Say the particle is somewhere here. Suppose the particle is somewhere here at this position. So particle reached at this position. So first of all I have moved say 1, the 2 and the 3 steps along x-axis. Right. So along x-axis say I moved 1, 2 and the 3 steps along x-axis. Then I moved along the y-axis, say parallel to y-axis, and I reached at this point, say 1, 2, 3 and the 4. This is the 4th position is here. It is 1, it is 2, 3 and the 4. And then I moved vertically upward like this. Say it is a z-axis, so I am moving upward in this way parallel to z-axis. right? So that means I finally reached at this point. Say this position is a 1, this is 2, this is 3, this is 4, this is 5, and so this is 6 position. So that means if particle is somewhere here, say this position is A, so A is basically along x-axis I moved 3 steps, and then along y-axis I moved 4 steps, and along z-axis I moved 6 steps. So that means this position vector is basically, say this position vector is this one. This is the R, is the position vector, and it is represented by 3, 4 and a 6. So that means I moved 3 steps along x-axis plus 4 steps along y-axis and 6 steps along z-axis. So z direction is represented by k vector. Let us assume that, because k vector is the, k cap is the unit vector along z-axis. So that means the direction along x-axis is represented by I cap, direction along this is represented by j cap I, and along z-axis it is represented by k vector. Now let us try to look at this particular problem. So that means, say if xy plane is represent the floor, so any line drawn perpendicular to floor, not perpendicular, parallel to z-axis is perpendicular to floor. So that means this is perpendicular to this one. This is perpendicular to this. Also, if I draw large number of lines, say it is a floor. Suppose this is a floor. This represents a floor. Any line which I have drawn, that is always perpendicular to z-axis. Say it is a z-axis, right? If I go to the room, or if I look at a room, basically, so let me take a certain example here to represent this. So this is basically a box, or this is a box, or this is a portion of a box with me. Let me take certain example. What should I do? Yeah, let me take example of book. So this is a book with me. So if you draw any line over it, because this is a z-axis, z-axis is here, this is z-axis. So if you draw any line, say if I draw one line over it, this is one line which I have drawn here, suppose. So this is always perpendicular to this z-axis. This is always perpendicular to it. If I put it like this, then this is also perpendicular to this z-axis. If I do it like this, then it is again perpendicular to this one. So that means what? We have to see it in a little bit different manner, so that things will not confuse me. So for that, let us redraw again the axis. So that means, say this is x-axis, say this is y-axis, and I have drawn like this two vectors, because it is like this, it is like this. So I am moving along the z-axis, because this is my z-axis. So first of all, this is say if I use this diagram, so it is 3i cap, and say from this I moved along the 4j cap. Then what this vector will be? Say this is another vector joining this, and let us call it as a row vector. So this row vector, because this vector is taken along this direction, this along this direction, so row vector is nothing but 3i cap and the 4j cap. And say the particle will be actually here. This is the actual position, and this is 6k cap. So this r vector is basically, because I have joined this row to this point, and this is again perpendicular to this. This is perpendicular because this is any line in the xy plane. This row vector is any line. Rather than line, call it as vector in xy plane. So this any line or in the any vector in the xy plane is always perpendicular to z axis. So that means this row vector plus 6k cap, because this row vector and 6k cap is along this, say row vector is this and 6k cap is basically along this direction. So both are taken in same order. Then the third closing side taken in opposite order is basically the resultant of these two. So that means this r vector can be represented as row vector plus 6k cap. But the row vector is basically this one. So therefore r vector comes out to be 3i cap, 4j cap and 6k cap. This is a way that how things can be represented in a three-dimensional space, or the position can be represented in a three-dimensional space. Now what should I do? Let me generalize it. So to generalize it, what I will do, this r vector is represented by xi cap, yj cap and zk cap. But if this is one position, this is another position of the particle, so this is a r1 vector, this is a r2 vector, this is the r2 vector. Say it is x-axis, it is y-axis and say it is a z-axis. Then the displacement vector is represented by r12 if we are moving from one point to the another point. This is the displacement vector. So this is the general representation of a particle in the three-dimensional space. So now if we are having two particles, one particle is at point A and another point at B, and this is the origin. So that means this A point is represented by it is A and it is B, and say this A point is represented by x1, y1 and z1, and similarly B point is represented by x2, y2 and z2. Then r1 vector is basically OA vector, and it can be represented as x1 I cap, x2 j cap, x3 k cap. Similarly r2 vector is represented by OB vector is equal to x2 I cap, I have mistaken somewhere here. Yeah, let me correct myself. Yeah, it is x1 I cap and y1 j cap and z1 k cap, and y2 j cap here and z2 k cap here. Then r12 is the displacement vector is represented by r2 minus r1 vector, as we have seen in for the case of the two-dimensional motion or the two-dimensional coordinate system. So similarly, if we do little algebra, then I vectors can be subtracted or added from the I and the j from the j and the k from the k. So it is represented by x2 minus x1 I cap and y2 minus y1 j cap and z2 minus z1 k cap. This is a way that how the position vector is represented in the three-dimensional space, and also the displacement vector is represented in the three-dimensional space. So I think that's all for today. In the next lecture I will talk about say that how the area can be calculated or the volume can be calculated in the Cartesian coordinate system. then I will switch to the other coordinate systems like polar coordinate system and the spherical polar coordinate system. So that's all for today's lecture.